Hello, everyone. So last time we were looking at the concept of derivatives and derivative rules, the rules that help us calculate derivative of any given function. So last time, derivative rules. And we did 11 properties. So 11th one was, derivative of exponential and logarithmic functions. And we saw that, the Euler number, how the Euler number can be defined. Euler number E, we defined it as limit 1 plus, let's say, x to power 1 over x. X approaches to 0 plus. And we saw f of x equals e to the x is differentiable everywhere. And f prime of x is equal to e to the x. And we also saw a limit of the form, let's say 1 to power infinity. 1 to power infinity is indeterminate and therefore needs simplification. Right, so 1 to power infinity, many people think it's 1, but because everything here is limit, so it's not, yes, if you say exact 1 to a large power, the answer is still 1, but limit 1 to a large power does not have to be 1. So for example, we saw that if you calculate 1.01 to power 100, the answer will be close to E, which is like 2.72 almost, right? So this is a number close to 1 raised to a large power. The answer will not be necessarily close to 1. So the limit does not have to be 1. The limit could be close to E in this case, or it could be other numbers. That's why we are saying it's indeterminate. Indeterminate means the answer could be anything potentially. And we have to simplify to find out what the answer is. So let's look at an example. Let's say find limit 1 plus 3 over n to power n as n goes to infinity. So the very first thing we can replace n with infinity, then what do we get? Then we get 1 plus 3 over infinity to power infinity. So that's 1 plus 0 to power infinity. That's 1 to power infinity. 1 to power infinity, we just said that is indeterminate. So how can we simplify? So we need to simplify. Now, how can we simplify? We are going to simplify this way. So what is the limit that we're asked to calculate? The limit is 1 plus 3 over n to power n goes to infinity. Now, if I call, let's say I want to use substitution. If I, let's say, define t to be 3 over n, then what? So remember, when you want to calculate the limit using substitution, if you want to substitute to a new variable, then you have to rewrite everything in terms of the new variable. So if you want to switch from n to t, then everything has to be in terms of t in the new limit. So you cannot have any n anymore. So 3 over n, I called it t, so 1 plus t to power n. Now what is n? Because t is 3 over n, so n will be 3 over t. So to power 3 over t, and t goes to what? So original limit says n goes to infinity. Now I'm switching to t, so in the new limit I should say t goes to which number? Where if n goes to infinity, t is 3 over n, goes to 3 over infinity, which is 0. As n goes to infinity, we can say t goes to 0. So limit 1 plus t to power 3 over t. T goes to 0. Now, how can I rewrite this? I can rewrite this as limit 1 plus t to power 1 over t. And the answer to power 3. T goes to 0 plus. Now we know that this limit inside exists. So then therefore I can write this one as limit 1 plus t to power 1 over t to power 3 as t goes to 0 plus, right? So here we use the fact that if limit like f of x to power 3, x approaches to a is equal to limit f of x approaches a to power 3 if limit f of x approaches to a exists. So this is a property of limits. And finally, we can write this one. So this limit is e, right? So this limit is e, we can replace it with e. Therefore, the answer will be e to power 3. Because limit 1 plus t to power 1 over t, t goes to 0 plus, is e. Okay, so let's look at another example. So in this case, we had, so that's why we're saying we have indeterminate. 1 to power infinity, when we say indeterminate, means the answer could be anything. The answer could be 0, could be e to power 3 like this case, or could be infinity. Let's look at another example. Let's say same expression as above, limit, let's say 1 plus 3 over n, this time to power n squared. N goes to infinity. Then what do we get? So the answer will be like, how can we simplify this time? So we saw in the previous example, we saw that limit 1 plus 3 over n to power n as n goes to infinity is equal to e cubed. So e cubed, how much is e cubed? Let's say roughly, e is almost 2.72. So you can use it to calculate e cubed, or you can directly enter e cubed in your calculator. E cubed will be a number close to 20. Okay, so as n gets larger and larger, this expression gets closer to e cubed, which is almost 20. So it's safe to say, it's safe to claim that this expression will be bigger than, for example, 2 for sure, after some n value. Right? After some n value, it will be for sure bigger than 2, because ultimately it will get closer and closer to 20, right? So if it's getting closer and closer to 20, then for sure it will become bigger than 2 after some value, right? So therefore we can conclude that thus we can say there exists, let's say, some n0 in n such that for n bigger than n0, we can say that 1 plus 3 over n to power n is bigger than 2. Okay, so what can we say about the final expression then? Look at the expression given in the question. So therefore we can conclude that we can say that 1 plus 3 over n to power n squared, which is what? Which is 1 plus 3 over n to power n, then the whole thing to power n will be bigger than 2 to power n. For again, n bigger than n0, right? Because the expression inside the bracket is bigger than 2, so the to power n will be bigger than 2 to power n. Therefore, what can we conclude? So as limit now 2 to power n, as n goes to infinity, what will be the limit? So the limit will be infinity, right? 2 to power infinity is infinity. So as limit 2 to power n as n goes to infinity equals infinity. What can we conclude? So see, this expression which is given to us is bigger than an expression whose limit is already infinity. So a number bigger than infinity must be definitely infinity as well, right? So as this limit is infinity, we can conclude that the limit given to us, 1 plus 3 over n to power n squared as n goes to infinity is equal to infinity. Okay, so this time it was a little bit tricky because, you know, previously in the previous example, we had limit of an expression to power 3, limit of expression exists. Therefore, we could say that, you know, to power 3, we could take the limit inside and just raise the answer of limit to power 3. But this time, situation a little bit different because the power here is not fixed. You know, we have 1 plus 3 over n to power n squared, which is 1 plus 3 over n to power n, then raised to power n. So in order to handle this, we compare this with some expression which is already infinity. In fact, 2 to power n, whose limit is already infinity as n goes to infinity. And we saw that, okay, this has to be bigger than 2 to power n because the expression inside approaches e cubed, which is almost 20 at infinity. So for large enough n, it will be bigger than 2 because it's going to get closer and closer to 20 ultimately. So of course, it will be bigger than 2 for at some point. Why did I use 2? You could use 3 because if it's getting closer and closer to 20 ultimately, it will be bigger than 2 or 3 or 5 or 10 or even 19, right? Even 20 because e cubed was 20 point something. So you could say also after some point, this expression is bigger than 20 as well. But even 2 is enough for me because I wanted to have some number which raised to power n gives me the limit infinity. Now 2 to power n as n goes to infinity gives me infinity limit, or 3 to power n, same thing, right? So so it doesn't matter, use 2 or 3, doesn't matter, or 10 or 19, whatever. But you cannot use 22, for example, because it's getting closer and closer to 20 e cubed, which is 20 point something. So it won't be bigger than 22, for example, right? But 2 or 3, these numbers. So 2 to power n now as n goes to infinity is infinity. Now we have an expression which is bigger than another expression which is already infinity. So we can say that the original limit is also infinity. This type of conclusion that we compare two expressions, one is already infinity, one is bigger than that. We say the bigger one is also infinity. So this is called a comparison test. You will see this in detail in Math 114 next semester. But for now, let's just state it informally and just say that, we have two expressions. One is infinity, one is bigger than that. So the bigger one must have the limit infinity as well. So I just gave you some examples of 1 to power infinity to show you that this is really indeterminate, meaning that the answer could be e or e cube or infinity or 0 in some cases. So depending on the type of the example and type of the limit. So let's also calculate, the derivative of a logarithmic function. So for logarithmic functions, or let me say derivative of logarithmic function, let's start with f of x equals ln x. Ln x, as you know, means logarithm x in base e. Note that f of x has, what is the domain? The domain of f of x is 0 to infinity, open interval 0 to infinity. And our claim is f of x is differentiable on the whole interval on its whole domain. F of x is differentiable on 0 to infinity, and f prime of x is equal to 1 over x. Okay, so let's see how we can prove this claim. Proof of the claim. So we want f prime of x, so we know that f prime of x is equal to limit f of x plus h minus f of x over h. H approaches to 0. Now, what is that going to be? So this is going to be limit ln x plus h minus ln x. F of x is ln x, right? F of x is ln x divided by h. H approaches to 0. And then this one, limit, we can use the log properties. We know that log a minus log b. Do you remember the formula for log a minus log b is equal to log a over b? So this one I can write it as limit 1 over h times ln x plus h over x as h approaches to 0. So now this is limit 1 over h ln 1 plus h over x. H approaches to 0. Now I can move h. First I can call h over x. I can use substitution. Let's say I call h over x as t. Let's see what would be the limit if I call it t. So we use a substitution, t equals h over x. Then what will be the limit in terms of t? If t is h over x, h will be, we have to find h. H will be xt. So then we will have limit 1 over h. So 1 over xt ln 1 plus t. T goes to what? Because a t is h over x. X is a fixed number here. X is a fixed number between 0 to infinity. And we know h goes to 0. If h goes to 0, so as h goes to 0, t goes to 0 as well, right? Because t is h over x, so t will go to 0 over x, and x is a fixed number. 0 over x, the limit will be 0. So t goes to 0 as well, right? And then, so this one, if we want to simplify, I can, 1 over x, I can take it out of the limit because limit is over t, x is considered as a fixed number. So 1 over t limit, sorry, 1 over x, I can take it out, the limit is over t. Limit 1 over t, I can take it to the power, right? Because we know that m ln a is equal to ln a to power m. So then this is 1 over x limit 1 plus t to power 1 over t. T goes to 0. And then this one, we can write it as, now this one, oh, there is also ln, so I forgot the ln. Limit ln of this, ln of this expression, ln 1 plus t to power 1 over t. Now this one, you know, the expression inside, we know that it has a limit. So this one, I can write it as 1 over x ln of limit 1 plus t to power 1 over t. Because we know that if the functions, everything is continuous, then we can take the limit inside, right? So we saw that property of limit before. And this limit is now e. So 1 over x ln e, and ln e is 1, right? Remember, ln means logarithm in base e. So ln e means logarithm e in base e, which is 1. So this 1 over x times 1, the answer will be 1 over x. So this one using basically, so we use the fact that limit, so one thing I want you to notice here is that this limit here is when t goes to 0. But we saw that if t goes to 0 plus, this limit is e. But what about if t goes to 0 minus? That can be also, it can be shown that that limit is also e, right? So right limit is e, we already stated as the definition. Left limit is also e, therefore the whole limit will be e. So let me say, using the fact that limit 1 plus t to power 1 over t, t goes to 0 plus is e, and the left limit is also e, 1 plus t to power 1 over t, t goes to 0 minus is also e. This one is by definition of e, this one was by definition, and this one, it can be shown. Let me say it can be shown. It's not by definition, but it can be shown that the left limit is also e, and so the whole limit is also e. Limit 1 plus t to power 1 over t, t goes to 0 is also e. All right, so what did we show? So we showed that f of x equals ln x is differentiable on 0 to infinity, and f prime of x is equal to 1 over x. So the question is, what about other logarithmic functions? Because ln x means logarithm in base e, but what about, let's say, if we have logarithm x in base 10, is that also differentiable? And if so, what is the derivative, right? So for the other logarithmic functions, so now let's say other logarithmic functions. Let's say we have a base E, for example, a base A, let's say let f of x equals logarithm x in base A. We know that base of the logarithm must be always positive and the base must be not equal to 1. Then how can we write f of x? Then we can write f of x as ln x divided by ln a using change of base formula. Change of base formula. So this is a formula you signed pre-calculus. Also, we had a review in the first lecture, right? So see the review lecture. See lecture 1, let me say, see lecture 1. Okay, so lecture 1, we stated about change of base formula, which we said that logarithm x in base A can be written as ln x divided by ln a. So now we already know the derivative of ln x. We are just multiplying it with 1 over ln a. So we can find f prime of x then. So thus f of x equals logarithm x in base A is differentiable on the interval 0 to infinity. And what about its derivative? And f prime of x is how much? We know that if you multiply a function with a constant, it does not change its differentiability, and the derivative of the new function is just the same constant times the original function. So f prime of x will be 1 over ln a times ln x derivative, and this means 1 over x times ln a. So if the original function is ln x, the derivative is 1 over x. If the original function is logarithm x in base A, then the derivative is 1 over x times ln a. So let's look at an example. Find the derivative of the following functions. So let's say part A, f of x equals ln x squared. Part B, f of x equals ln 2x. So solution for part A, f of x equals ln x squared. I can just use the log properties. Ln x squared, I can write it as 2 times ln x. Why? Because we know that ln x to power m is equal to m times ln x, right? So ln x squared, I can write it as 2 times ln x. And therefore, f prime of x, I can easily calculate it. F prime of x will be derivative of 2 times ln x. Now, a constant times the function derivative, I can just take the constant out. So 2 comes out, and then derivative of ln x. Derivative of ln x, we know is 1 over x. So 2 times 1 over x, and the answer is 2 over x. For part B, ln, what is it? ln 2x. F of x is equal to ln 2x. Now again, we can use the log properties. We know that log AB is equal to log A plus log B. So this one I can write it as ln 2 plus ln x. So f of x, we wrote it as sum of 2 functions, and derivative of sum of 2 functions is the sum of derivative of those 2 functions. So that means f prime of x is equal to ln2 derivative plus ln x derivative. ln2 derivative, we know it's 0. So d to dx of c is equal to 0 for a constant c. And then this means it's 0 plus ln x derivative. The answer is 1 over x. Okay, so we could calculate derivative of these two functions. But another approach to calculate derivative of these functions is to look at f of x as composition of two functions. And if we can derive a formula for derivative of composition of two functions, then we can also calculate f prime of x that way, okay? But unfortunately, so far, we haven't stated a formula for derivative of composition of two functions. But don't worry, that's our next goal. I'm going to state the formula shortly for you. So maybe I can state a remark here is that in part A, we can write f of x as, let's say, g of h of x, where g of x is equal to ln x and h of x is equal to x squared. Similarly, in part B, we can write f of x as g of, let's say, k of x, for example, again, where g of x is ln x and k of x is 2x. Right? So that means if we derive a formula for the derivative of composition of two functions, then we can compute f prime of x. Okay, so that's our, so far we derived formulas for derivative of sum of two functions, or a function times a constant, or multiplication of two functions, or division of two functions. So those things we have done, but composition of two functions we haven't done yet, and that's a very important formula. So next property, I think property 12. So far we stated 11 properties. Property 12. Chain rule. Derivative of composition of two functions. So let me state the chain rule or derivative of composition of two functions for you. So let f of x and g of x be two functions. Then h of x defined as f of g of x is differentiable and h prime of x, so d to dx of h of x, or h prime of x, is equal to g prime of x times f prime of g of x. So this is chain rule. Derivative of f of g of x is g prime of x times f prime of g of x. Okay, so many people think that, f of g of x derivative is f prime of g of x, but that's not true. F of g of x derivative is g prime of x times f prime of g of x. So in other notation for this, let me say other notations. Other notations for chain rule. So one notation, one simple notation is that if I set u equals g of x, right? Then f of g of x will be f of u. And hence the chain rule can be written as follows. D to dx of f of u, because the left hand side d to dx of h of x, but h of x means f of g of x. F of g of x means f of u, which is f of u derivative. I can write this one as u prime times f prime of u. F of u derivative is u prime times f prime of u, right? Because g prime of x, g of x, I called it u in this notation. So g prime of x will be replaced by u prime. F prime of g of x will be replaced by f prime of u, because again, g of x, I'm calling it u. Okay, and one other notation, another notation for chain rule, another notation, or Leibniz, basically Leibniz notation. So chain rule in Leibniz notation or with Leibniz notation. So how can I write it in this form? So if I set y equals f of u, this is f of g of x, which is f of u. Then what can we say? Then we can say dy to dx. See, left hand side, what is left hand side? D to dx of f of u, right? Here, look at here, d to dx of f of u. But f of u, I'm calling it y. So then I can say dy to dx is equal to, now this term here is dy to du, because it's derivative of f. I'm calling it y respect to u, right? So dy to du times u prime. U prime is dy to dx times du to dx. See, that's why Leibniz notation is very convenient. So if you look at the right-hand side, dy to du times du to dx, it's as if you had two fractions and like du cancels with du. But of course, this cannot be considered as a proof, right? Because dy to du is just a notation for derivative, and du to dx is just a notation for derivative of u respect to x. This one a notation for derivative of y respect to u, right? So these are not, you cannot say I want to cancel this du with this u, because it's just a notation. But why do we like this notation, or why is this notation so common? Because it behaves as if it was a fraction. So it shows similar features as fractions, and everyone knows how to work with fractions, right? So everyone knows that if there were two fractions here, du would be canceled with du, the answer would be dy to dx, right? Everyone would know that. But this one, although it's not a fraction, but it behaves as if it was a fraction. Still, we can say dy to du times du to dx is dy to dx. So that's why we like this notation. This notation is very common in all textbooks because it has a nice feature that in order to predict the result, you could imagine that if this was a fraction, what would happen? But if this was a fraction, we would be able to cancel du with du. The answer would be this. So, but right now, although it's not a fraction, but because it behaves like that, so still we can predict that the answer must be dy to dx, but that's just a prediction, or just an intuitive idea, basically, or intuitive reason. The formal proof is, of course, not as simple as this. For the formal proof, we need to use the limit definition of derivative, right? We did a formal proof using limit definition for product rule and quotient rule. But this one, the formal proof is a little bit more complicated. I want to skip it, but you will learn it in analysis 1. If you take math 225 analysis 1, you will learn the proof for chain rule in that course. Okay, so for now, we just want to understand the concept and the application for chain rule. For the proof of chain rule, I'll refer you to 225 or analysis 1 course. So this one, chain rule in Leibniz notation. Chain rule in Leibniz notation. Okay, so proof of chain rule. Proof of chain rule, as I said, you'll skip it. You'll see in math 225. Okay, so I stated 3 notations for chain rule for you. The simplest one, dy to dx, is dy to du times du to dx. Another notation, f of u derivative is u prime times f prime of u. Another notation, f prime of g, or f of g of x, the whole derivative. You can also write this one this way, that maybe I can write it this way, that f of g of x, the whole derivative, because this is derivative of h of x. H of x is f of g of x. So f of g of x, the whole derivative, is g prime of x times f prime of g of x. So all these 3 notations are common and can be useful depending on your preference and depending on the type of example. The proof we said we will skip. So what we have to do, some examples, there can be many important examples can be done with chain rule.